at DeepSound.AI, and today I want to present our recent work, Conversational RuBERT, for detecting competitive interruptions in ASR-Transcribed dialogues. First of all, I want to say that the application area of our work is machine learning in communications, more specifically conversation analytics in contact center monitoring. And in order to better understand this presentation, we need to discuss some introductory questions. What is interruption in conversation analysis? What is contact center monitoring? And how can conversation analysis can be applied in it? Let's start with the definition. Here you can see the quote. Interruptions can be seen as situations in which one person intends to continue speaking, but is forced by the other person to stop speaking, at least temporarily, or the continuity or regularity of that person's speech is disrupted. There are two general types of interruptions, cooperative and competitive. Competitive interruptions can include disagreement, floor taking, topic changing, while cooperative interruptions include agreement, assistance, or clarification. As we are talking about data science, we want to know what data types, so data features can be used in order to differentiate between these two types of interruptions. And I added two options. First of all, we can use audio features as, for example, prosody, pitch, loudness, intensity, speech rate, and disfluency. But also we can try to use some lexical and linguistic features. What is contact center monitoring? It involves collecting, analyzing, and evaluating data from customer interactions to improve service quality, agent performance, and customer experience. So how can we apply conversational analytics? Conversation analytics allows us to assess the quality of service provided by agents, and we can call it the task of agent monitoring. And on the other hand, it allows us to understand the emotion, intent, and sentiment from every customer. And we can call it the task of customer satisfaction monitoring. Specifically, in our case, if we can detect interruptions, competitive interruptions, it can help us to detect aggression and impolite behavior during a conversation, which is very important for the both tasks. So now we understand that we want to develop a machine learning model to automatically detect competitive interruptions in calls. Let's talk about some parameters of this task. First of all, we use only dyadic speech, meaning that meetings are beyond the scope. We use only situations when two persons are interacting with each other. The second point is that we have a telephone conversation. It means that speakers do not see each other, and data like video recordings, we cannot use it. The third point is that we imply that our data is of sufficient quality, meaning that there is no need for extensive pre-processing step. In particular, we do not need the speaker diarization for our audio because we have separate channels for each speaker. And finally, we assume that our conversations are transcribed by ASR system, meaning that we have not only audio representation, but also the text of our conversations. Let's think how this model can be applied. At the first step, speech overlaps should be automatically extracted from a call. And then our model should take audio clips and their transcriptions corresponding to these overlaps as an input. This model should classify each episode, each overlap, as, for example, competitive or non-competitive. And these interruption statistics produced by this model can be collected and can be used in the downstream tasks, as we discussed in the previous slides. And now let's move to the related work. We identified 4 key aspects in the related literature: definitions of classes, data representation, representation of the speaker's context, and machine learning methods. Let's start with definitions of classes. We found that there are 2 groups of work. The papers in the first group utilized simple taxonomy consisting of 2 or 3 classes. For example, competitive versus non-competitive interruptions, competitive and cooperative interruptions and backchannels, and interruptions, turn changes, and backchannels. And the second group of works, these papers, the researchers in the papers elaborated via the taxonomy consisting even of 12 classes, but we want to start from the simplest situation, and we want to use simple taxonomy. The second key aspect is the form of data, and we found that the most of work utilized audio representation. Few works additionally experimented with the combination of audio and textual features, and very few works tried to use textual features only. And I think this is a point for potential improvement. Next, let's talk about representation of the speaker's context. There are 3 criteria that we found. The first criteria is about minimal duration of an overlap. For example, if we are talking about audio, we want all overlaps they must last at least X seconds, or they must contain at least X words. And different researchers offered different threshold values for this X. The second criteria, it's about the duration of an overlap. Having an overlap, which part of it we want to feed into the model. We want to, for example, we can feed only the first 5 seconds, 10 seconds, or 20 seconds. And if we're talking about textual representation, we can use only first 5 words, 10 words, and so on. And there are many options in the related work. And finally, overlap context. Some researchers experimented with using only interrupters turn and the turns of the interrupter and the speaker. And also one more interesting option is to use some vicinity. For example, if there is an overlap, we may want to add to the model some preceding turns and some consequent turns, so the model can have a wider context. The next key aspect, it's about machine learning methods. We found classical machine learning models like SVM, random forests, K-means, common neural networks as feed-forward, recurrent, and convolutional. As for NLP methods, we found classical bag of words, bag of n-grams, and word-to-vec. And in recent studies, we encountered large models such as WaveLM, BERT, and GPT. And it should be noted that BERT was used not for the task of interruption classification, but for the task of backchannel prediction, which is quite similar. Next, let's talk about materials and methods that we used in our experiments, and let's start with the data set. We assume that we use ASR transcriptions, and an ASR system contains voice activity detector, which separate turns in a conversation. It means that in a table produced by ASR system, each row corresponds to a turn in a dialogue, and it is characterized by the channel of the speaker, the timestamps of its start and end, and the transcription. If we concatenate two consequent turns to each other, we can compute some additional features which are important for us. First of all, we want to understand the type of the turn change. Was it an interruption, or it was just a gap? If the second person started speaking after that the first person ended the speech, it means that it's a gap, there is a pause between the speakers, and it's not of the interest for our work. Otherwise, if we had an instance of simultaneous speech, it's an overlap. And for each overlap, we can calculate its successfulness. It means that the first speaker stopped their speech before the second speaker did it. It means that the interrupter overtook the turn and it was a successful attempt. Otherwise, it was unsuccessful attempt. We can compute the duration of an overlap based on the timestamps. And we also want to know who was in role of the interrupter. Was it a client or an agent? And we can know this information from the channel. Now, when we have a row corresponding to a overlap instance, it is characterized by the interrupter, who was the interrupter, its successfulness, its duration, and the transcriptions for the both speakers. Now we want to filtrate and label our data set. First of all, we use only the simplest case. We want to start from competitive versus non-competitive interruptions. And during filtration, at the first step we removed all unsuccessful attempts. At the second step, we removed all overlaps lasting less than 1 second, trying to discard all unintentional overlaps like simultaneous start, back channels, and so on. And we want to preserve interruptions caused by both clients and agents, because both cases are of interest for the task of call center monitoring. And the labeling process was organized as follows. For each overlap, an annotator listened to the part of the audio containing this overlap. This overlap was labeled as competitive, non-competitive, or undefined if annotators could not unambiguously decide between classes. And we removed all undefined overlaps from the data. Here you can see the distribution of classes across speakers, and you can notice that the amount of undefined samples is significant enough, meaning that maybe our binary classification system is too simple for the task. Maybe we need something more complex. And now let's talk about the choice of model architecture. The first consideration is that large language models received little attention regarding the task of interruption classification, and we know it from the related works section. One of these models, RuBERT, was used in the similar task of predicting back channels, and it showed good results. So the idea, why not to try to use this architecture for our task? Moreover, RuBERT is less resource consuming than GPT, which was used in one of the recent studies. And this is very important for potential industrial applications. And finally, as our data set, it's transcribed Russian speech, we want to use the conversational RuBERT developed by Deep Pavlov team. Here you can see models hyperparameters. They are quite basic. As we are talking about classification problem, we applied Claros entropy loss. We used the default optimizer and scheduler. And as we use a pre-trained model, we want only to fine-tune it, and that's why we do not need lots of epochs. As for metrics, we applied standard classification metrics such as area under curve, F1, recall, precision, and they all are important because they reflect different nuances. Now let's talk about training and evaluation process. First of all, we provided cross-validation on 9 faults. Specifically for each validation fault, we fine-tuned the model on 8 faults and pick up the best checkpoint across the training steps based on area under curve on the validation fault. Then we performed threshold moving based on F1 averaged across 9 validation faults. Then we made testing on the holdout fault. For each of the 9 best checkpoints, we computed F1 on the test fault using the adjusted threshold and relevant checkpoint. And we report the final metric as F1 averaged across 9 best checkpoints. Now let's talk about experiments. In the first experiments, we want to understand the influence of the speaker's turn. That's why in the first setting, we fed into the model only the interrupter's turn, while in the second setting, we gave to the model the turns of both speakers, both persons. In the second experiment, we adjusted the learning rate, and finally, we tried to understand the influence of additional context. What will it help to the model if we concatenate to the turns, if we concatenate preceding context to the beginning of the first speaker's turn and the following context to the end of the second speaker turns. Here you can see result and best hyperparameter set. The best option in the best option, our model takes a pair of turns for both speakers. Unfortunately, additional contexts are only drastically decreased the quality, and you can see the best learning rate. And you can see the model's performance. It's quite good with F1 equals to 0.84. Now let's talk about limitations of our work. The first group of limitation is due to the filtration process. First, we discarded all unsuccessful attempts, and maybe they can be informative regarding the intention of the interrupter, despite being unsuccessful. Maybe we can add it into our data set. The second is the duration threshold. Maybe it is too high and discard lots of samples from the data, and it can be optimized experimentally. The second group of limitation is due to the labeling process. We discarded samples labeled as undefined, and in an ideal situation, we need to include them into the data. Maybe we can separate them into the third class, or maybe annotators should decide between the two classes. And of course, our labeling process was as simple as it can be. meaning that one sample was annotated by one person and only one time. And this design does not allow to compute intra or inter-annotator consistency, and it can make our labels too subjective, depending on the annotator's opinion. And finally, regarding our model's performance, it's quite good, but of course we want the better performance, especially if we are talking about industrial application of the model that based on which agents, the performance of people working in customer service should be estimated. Of course, we want as high accuracy and as possible. There are two possible improvements. First of all, more complex labeling process, including unsuccessful attempts and overlaps lasting less than 1 second. But we should understand that this make this process too resource consuming, because we need more people to annotate. We need more time to spend on this task. And also there is a possibility to combine the model with an audio-based model. As I said before, the most of the work dedicated to the topic utilized audio-based model, and I'm sure that if we combine text-based and audio-based models, we will increase the performance. Now I want to summarize my presentation. In this study, we formulated the business needs for detecting interruptions as a machine learning task. We systematized the literature and found room for improvement. We collected and labeled the in-house dataset of ASR-Transcribed contact center calls between agents and customers. We fine-tuned model and provided hyperparameter optimization. The model achieved good performance, and we proposed steps for further improvement, namely more complex labeling process and combination with an audio-based model. That's all. Thank you for your attention.
Yeah, thank you for your presentation.